Hello everyone, I am Akila Herath. In this presentation, I will talk you through about the lab demonstration on cyber physical system security testbed for substation automation. So currently I am a PhD student at the Power and Energy Center of Virginia Tech and I am working under the supervision of Dr. Chenchil Liu, and these are some of my research interests. So this is the outline of this presentation. First up, it's the introduction. Then I'll talk about security vulnerabilities in IC 61850 SV and Goose, which is actually the base of this research. And then the overview of the test bed. Then I'll introduce the test setup for this demonstration. Then I'll demonstrate some normal operations and some cyber attacks with this test bed. And finally, it'll be the concluding remarks. So, over the past decade, cyber attacks have increasingly targeted electrical power grids, with substations being a primary focus. Now, keeping this fact aside, we have also observed the emergence of the integration of more and more ICT into power grid, and with that, we have observed the implementation of IC 61850 for substation automation, which improved the power grid management efficiency. However, this has also exposed the modern power systems to cyber vulnerabilities. Now, to strengthen the substation security, particularly in IC 61850 based substations, considerable efforts are being made on developing strategies for cyber intrusion detection and mitigation. To validate these proposed mitigation and detection methods, cyber physical system test beds are commonly used, and the major focus of these test beds are to replicate the cyber physical interactions in an actual substation environment. So now I'll talk about the security vulnerabilities in IC 61850 based SVN Goose. IC 61850 is an international standard for the automation of electrical substations, providing a comprehensive framework for communication, information modeling, and system architecture. And under that, we have these SVN Goose communication protocols, which are mainly defined for time critical operations such as circuit break operation. Goose is used for fast and reliable transmission of protection and control messages, and SV is essentially used for transmitting time synchronized sample value measurements. Now, if you look at this figure 1, you see the CTs and VTs in the physical layer sends measurements to the merging unit, and merging unit sends these measurements to the protection and control ID as SV. And if the protection and control ID see any requirement of a circuit break operation, it sends a goose to the merging unit, and merging units conveys this to the circuit breaker. Now, to address these time critical requirements, Goose and SV are formed as layer 2 protocols that follow a publisher subscriber communication model, such that they lack IP level security and they don't even have any kind of built-in authentication or encryption in their standard forms. If an adversary gained entry into the substation local area network, the adversary can easily manipulate the circuit breaker operation by intercepting SV and Goose packets and simply injecting them back with modifications. This is the overview of the hardware in the loop cyber physical system security test bed in our lab, built with industry grade devices, typical in an IC 61850 based substation. The physical layer of the power system is modeled using a real-time digital simulator. The merging unit ID, which is connected to the real-time digital simulator via an amplifier, translates the hardwired communication signals into Ethernet based data packets and vice versa. The data sent by the merging unit ID is received by two protection and control IDs in the bay level, in between the process bus and station bus. At the station level, we have an RTU which is integrated with an HMI. Actually, the RTU serves as a communication node between the substation and the control center. Then we also have a GPS clock which is used to synchronize the substation device's time with the use of IEEE PTP protocol. We also have these three modules which are programmed with the C-based libic61850 open source library. This attacker module is actually capable of capturing SV and goose packets in the network, and it can generate goose and SV based attacks. And the network intrusion detection system we have in this testbed is actually based on an rule based algorithm which applies SV and goose protocol rules, and this IDS actually sends out a goose message when it detects any kind of an intrusion. Then we also have a simulated ID integrated into this test bed, and actually simulated ID can mimic the functionalities of a real protection and control ID. For this demonstration, the setup shown in this slide is used. So in this setup, we have the merging unit ID, which communicates with one protection and control ID via the process bus. And as the power system is modeled in the real-time digital simulator, and as the power system model, we have this two bus model where the current and voltage of a feeder is monitored, and there we also have a circuit breaker and a fault point to create faults. Normal operations demonstration. Now here I am demonstrating the circuit break operation with IC61850, and here by pressing this press button actually I am creating a three-phase to ground fault in the power system. And actually with that fault, now in this top plot which you are seeing the feeder current, you can see a fault current, and you see it takes like one complete cycle for the circuit breaker operation. And in this bottom plot you see the statuses of the fault signal and the goose strip as well as the circuit breaker operation. So what happens initially is this: in the blue line you can see the fault signal, and after the fault signal there is a slight delay in between the fault signal and the goose strip signal. This delay is actually the time taken by the protection and control ID to detect the fault with the use of the received SV, and this delay we found it as an average value of 13 milliseconds. And then between this green line and red line there is another delay. Actually this delay is the delay at the merging unit to operate the circuit breaker, and this value we found it as an average value of 6 milliseconds with our simulations with our test bed. So this is the cyber attack demonstration of a goose replay attack. In this attack, the adversary initially captures a goose packet which is originally sent to operate the circuit breaker. Later, adversary sends this goose packet back to the network when the system is in normal operation. Merging unit ID receives this malicious goose packet and sends a circuit breaker trip signal, and eventually the circuit breaker operates. Now here I am showing you the Wireshark capture I obtained when I am simulating this replay attack in our test bed. So, and here actually I am showing you the attacker module interface. Now here you can see that when the system is in normal operation, RTDS sends the circuit breaker statuses, and in these statuses you can see a bit string value of 80. A bit string value of 80 actually represents a normal operation. And now I am initiating the goose replay attack. Now you see what will happen is that these MAC addresses actually represents the attacker module, and that is actually the attack message. And straight after the attack message you see this MAC address which actually represents the goose message sent out by the network intrusion detection system which we have integrated in our test system. So this shows that the network intrusion detection system identified this attack. And then you see the circuit breaker statuses received from the RTDS showing a bit string value of 40. So bit string value of 40 represents that the circuit breaker is now open. So this basically shows that we have sent some malicious goose packets back to the network, and it caused to operate the circuit breaker in the power system. So this is the feeder current plot which we have obtained from the RTDS software, and here you can see that system is actually experiencing a normal current, but without any fault current. You can see the operation of the circuit breaker, and this is just purely because of the goose replay attack which we simulated. So this is the demonstration of an SV false data injection attack. Here again the adversary initially captures sample values from the substation local area network and identify their semantics. Then the adversary injects SV back to the process bias with false current measurements. In these simulations, we are injecting false data with high current measurements. Then the protection and control ID reads these false data and detects them as a fault, and then sends goose to the merging unit. Then merging unit sends a circuit breaker trip signal, and eventually the circuit breaker operates. Now again I am showing the Wireshark capture and the interface of the attacker module I captured when conducting these simulations. So here at the start you can see when the system is in normal mode, you can see the SV packets received from the merging unit, and here you can see the RTDS showing the circuit breaker status with this 80 value, which shows that the circuit breaker is currently closed. Now I am conducting this cyber attack with publishing this malicious SV into the network continuously, and now you see in this SV capture you can see some malicious SV MAC addresses as well. And now if we go back to this goose capture, you can see now these goose packets received from the circuit breaker which represent the circuit breaker are with this value of 40, which basically says that now the circuit breaker is open. So this again shows that this false data injection attack caused to open the circuit breaker in the substation which we are simulating inside the RTDS. This is an image we obtained from the interface of the protection and control ID, and actually this shows the calculated RMS current log in the protection and control ID during the period which we created that SV false data injection attack. And the time period which shown by this green indicator is the time period which we haven't done any kind of an attack, and that period you see a calculated RMS current closer to 200. And this time period which shows with this blue block is the time period which we injected false data, and that period the calculated RMS current is in the range of kiloampere, and this clearly shows the impact on the calculated RMS currents inside the protection and control IED with this SV false data injection attack. Including remarks. The presented cyber-physical security testbed demonstrated its capability to obtain realistic insights into cyber-physical interactions, which is actually critical for cyber-security studies. And we have also presented SV and Goose-based cyber attacks executed through the attacker module alongside the operation of the network-based intrusion detection system. And actually, the demonstrated attacks highlighted the vulnerability of SV and Goose for intrusions conducted by an adversary who gained the access to the substation local area network. And ongoing research with the testbed focuses on detection, mitigation, and recovery of cyber attacks in substations. Thank you for your attention.